Okay, in this video I'm going to talk about how we can find volume of areas that have been rotated about a specific axis. So the first method that we're going to talk about in this video is what I'm going to talk about is the disk method. So what we're going to do is I want to first find the region under the curve of y equals square root of x from 0 to 1. So this is y equals square root of x from 0 to 1 would give me this region right here. So if I were to fill this region in, this is what it would look like. So back to area between curves, if I just wanted to find the area between the curve, that I would use an integral and set this up, and I would find this area underneath this curve. But I want to find the volume if I take this and I rotate this about the x-axis. So what I'm going to do is I'm always going to replicate the graph going the opposite direction. So I want to try to, the best I can, draw this graph on the other side of the x-axis as well, which would give me something like this. And I'm going to go ahead and fill that in as well. And so I'm going to have this three-dimensional shape here where I've rotated this area underneath the curve, y equals square root of x, the area between 0 and 1 of that graph. And I get this three-dimensional thing. The best way to make it look three-dimensional, I suppose, and I just erased that, did not mean to do that, would be to kind of try to make this look like as if it were a three-dimensional thing, so that I can see what's going on. Okay, so I have something like that. I'm going to go ahead and color this back in, where I have this three-dimensional shape. Now this shape, as you can see, would be a solid shape. Okay, it would actually be completely 100% solid. Kind of looks like a gumdrop or something. And what I want is the volume of this shape. And so here's how I'm going to think about this. I'm going to think about slicing this shape vertically. Okay. And if I slice it, and I slice it thin enough, that's what we need to think. It needs to be sliced really, really thin. What I would end up with, see if I can do this, is I would end up with a bunch of, it would be helpful if I used maybe a different color here. I would end up with a bunch of circles just stacked on top of one another. So if I just keep on slicing this, I keep on getting more and more of these circles where they're just keep on, I just keep on stacking them on top of one another until I get this exact shape. Okay, so if you can visualize that, that's what we've got going on. A bunch of circles stacked from here all the way to here, and I just stack them up and I get this solid shape. So to evaluate the volume, all I need to think about is if I take the area of each one of these circles and I add all of those areas up, I would have, you know, that solid shape, three-dimensional, which would give me a volume. So for a disk method, you always want to think pi r squared. Okay, I'm going to add up a bunch of areas of circles. So I'm going to take pi r squared. I'm going to add all those up. So that's why you get the integral. The integral of pi. I want to think of it as r, but pi r squared. Except usually our radius, and I'm just going to write radius first. Usually our radius is going to be determined by the function. It may be defined by different things, but I'm going to have pi times the radius squared and then dx. Now the dx is the thickness of each one of these circles, so they have to have a little bit of a thickness to them, but I want to think of them as being really thin, so I can think of it almost as just adding up these very, very, very thin circles where the width of the circles is, or I should say the width of the it would be cylinders at that point, is very, very minimal, and I can kind of negate that, and I don't need to worry about it. So that's what I want to think about with the disk method. Pi times the radius squared, and then the integral, if I do the integral from a to b of that, that means I take all of these pi times radius squareds and I add all of them up from a to b. That's all that says. So in this case, I'm going to do the integral from 0 to 1. And how do I get 0 to 1? Well, when I start slicing these things vertically, my first circle is going to be at 0, my last circle is going to be at 1. So I'm going to have all those circles stacked up from 0 to 1. I'm going to go ahead and take the pi and I'm going to factor that out front so I can deal with that at the end. And then I just have to figure out what the radius is, and I'm going to square it. So if I think about the radius of each one of these circles, the radius is just going to be from the x-axis to the height of the circle here, which is just going to be to the function. So my radius, and this is going to be the case most of the time, is just going to be the function. I'm going to square that, and then I'm going to multiply by dx. You would want to simplify this, so this will be pi times the integral from 0 to 1 of x dx. Whenever I square the square root of x, I just get x. And now I can evaluate this. This is a very simple example. The antiderivative of x is 1/2 x squared, and I'm going to evaluate that from 0 to 1. So I get pi times 1/2 times 1 squared minus 1/2 times 0 squared, which will give me pi times 1/2 minus 0, which is just going to be pi over 2. Okay, so keep in mind that's the volume of this shape. Pi over 2, I could say cubic units to give me that three-dimensional volume. But that's all you're doing. So always think pi r squared with this method and figure out which way the circles are going to be stacked. That's going to give you these bounds, 0 to 1, and then figure out what the radius is.